Welcome to PhysicsNextBook. In this video, we shall derive the Lagrange's equation by applying the principle of least action for mechanical systems. In our last video, we introduced the concept of action for a system and discussed the action principle or the principle of least action. We saw what the statement of the principle means mathematically in context of particle mechanics. So, let's watch the action principle leading us to the Lagrange's equation, which in context of particle mechanics will turn out to be the equation of motion of a particle we get from Newton's second law. You must be thinking, why should we bother with the action principle and Lagrange's equation when it is telling us what we already know? But the applicability of the action principle and the Lagrange's equation go way beyond. You see, Sir Newton's laws are only applicable to objects that have mass. That is, we can get the dynamics or time evolution of a massive object from Newton's law. But the action principle through the Lagrange's equation can reveal the time evolution of any system. Massive objects, massless ones like a photon, even the time evolution of electric, magnetic and gravitational fields. It is indeed a big deal. So before we begin, you may want to watch the video on the action principle from the link if that stuff is new to you. Okay, let's jump in. In its very general form, which is suitable for any given mechanics problem, the action is written as a time integral between the initial and final time of a function that we call the Lagrangian for the system and symbolized with the letter L. The system can be anything under the purview of mechanics, as simple as a free particle or one falling under the Earth's gravitational pull or doing a projectile motion or oscillating, or it can be a bit more complex like a charged particle moving in a magnetic field and so on. The Lagrangian function for all these different systems will of course be different, but the general structure of the Lagrange's equation we are going to obtain from the very generic action integral remains the same. Now, we said the Lagrangian is a function, but a function of what? What should it depend on? Well, since it is mechanics we are dealing with, we know what the relevant variables are: the position of the particle, its velocity, acceleration, etc. So basically x and its time derivatives. By the way, to make it look simpler, physicists often add a dot on a variable to denote time derivative. So 2 dots means second derivative of time and so on. But can there be higher orders of time derivatives? For example, why not include d3x, dt3 and so on? How do we know where to stop? For this, we can take a hint from the Newton's force equation, which, as we know, involves only up to second order time derivatives of x, that is x double dot. The Lagrange's equation, which we are aiming for, should thus also be a second order differential equation of time. That happens only if we take the Lagrangian as a function of x and its first derivative. In some cases where a time varying force is acting on the particle, its time coordinate also creeps into the Lagrangian. These are called open systems, but we shall not go into that today. In the rest of the particle mechanics scenarios, the Lagrangian is a function of the particle's position x of t and velocity x dot. As you may have guessed, these are called closed systems. Anyway, if you have been a regular to this channel, you already know that position as a function of time represents a trajectory and different functions mean different trajectories. Since the Lagrangian is a function of x and x dot, for every possible trajectory function x of t, we can calculate the corresponding x dot as a function of time and then substitute both the functions in the Lagrangian to make it an explicit function of time. Now, the time integral in the action can be carried out between the limits set by the initial and final time. So given a trajectory function x of t and the initial and final event points, action takes a numerical value, justifying the statement action is a function of a function or functional. Refer to the video on the action principle for detailed discussion on this. According to this action principle, among all the possible trajectories that a particle may travel through, it chooses the one for which the numerical value of the action remains stationary. The word stationary means if the path is changed slightly, let's say from x of t to x of t plus delta x of t, the resultant change in the value of the action delta A is insignificant. So, can we calculate the numerical values of the action for all the different trajectories to identify the stationary one? It will be a futile exercise since there are infinitely many possible trajectories and, well, it's just too much hard work, really. Instead, we apply a trick which goes by the name of variational principle or the calculus of variation. The idea here is to not go for any specific function x of t, but keep it completely generic and of course between the given pair of initial and final event points. Calculus provides us a way to calculate the change in the action delta A for infinitesimal change in this generic path from x of t to x of t plus delta x of t being the change of the path. We did this in the last video without specifying what the action functional looks like. But this time, let's do it with the action written as a time integral over the Lagrangian, which itself is a function of x and x dot. Before we proceed, let me point out that till we solve the problem and find the actual path function x of t, that is the solution to the problem, we cannot calculate its time derivative dx dt or x dot either. So dx dt should be treated as an independent variable. Innocent until proven guilty, that sort of logic. Now let's calculate this change in the action delta A. Notice that if the trajectory x of t is changed, dx dt or x dot, which is basically the tangent to the trajectory at every t, also changes. See, the slopes of the two tangents differ, right? Now, the action is a time integral of the Lagrangian. So, the change of the action due to the change of trajectory should be the time integral of the change in the Lagrangian delta L. Since L is a function of two variables x and x dot, its total change is the rate of change of L with x times delta x, the change in x, plus the rate of change of L with x dot times delta x dot, that is the change in x dot. Here, instead of the usual d symbol, the derivatives are written with a del symbol indicating partial derivatives of L, since L is a function of two variables x and x dot. Now, the action principle says that the variation in the action delta A, calculated up to the accuracy of first order in delta x, should vanish for any arbitrary path variation delta x if the path x of t being varied happens to be the stationary one. So we work this logic backward and find the mathematical condition for the correct path by equating the delta A to 0 for arbitrary delta x. This means the delta x needs to be factored out from the expression of delta A, and what is left is to be equated to 0. In a while, you will see that this gives us a differential equation, solution to which is the path function the particle actually follows. However, we cannot factor out the delta x from what we have here as the expression of delta A. Not yet, because in the second term there is a delta of x dot or delta of dx dt, not delta x. Luckily, calculus has a magic trick that saves the day. It says, going a small distance dx along the path and then shifting to the slightly changed path is same as shifting to the changed path first and then going a small distance dx along it. As long as we are dealing with infinitesimals like dx and delta x, we get to the same point finally. This basically means delta of dx dt is the same as ddt of delta x. Notice the use of symbols here. Delta symbolizes the change of path and d symbolizes changing position along a path. So, in the expression of delta A, we can replace the delta x dot by ddt of delta x in the second term. Now we can manipulate the second term to pull out the ddt and put it over the whole second term to make it a total time derivative. But this brings an extra term into the mix, which we have to subtract. Thus, the second term has been re-expressed as a total time derivative term minus another term where the delta x is freely available for us to factor out. Remember, all this has been happening inside our time integral, right? So we can readily perform the time integral over the total time derivative term between the integration limits. This yields del L del x dot times delta x evaluated at the initial and final time instant. Now, if you have watched our last video carefully, you would know that when we change the generic path x of t infinitesimally, we must keep the initial and final spacetime location of the system unchanged. So the path variation delta x of t should be such that delta x of t at t initial and delta x of t at t final are both 0. Therefore, the integral of the total time derivative term does not contribute anything, and we are left with a term where factoring out the delta x is totally sorted. So the full expression for delta A we had written earlier has now been manipulated into a suitable form where we can take the delta x out and equate the rest to 0 to impose the condition for the stationary action. This complicated looking equation is called the Lagrange's equation. So we have got what we wanted. It can produce the equation of motion for any closed mechanical system for which we know the specific form of the Lagrangian L in terms of the two variables, namely the position x and the velocity x dot. Luckily, for non-relativistic closed mechanical systems like a slowly moving free particle or a standard harmonic oscillator or a particle falling under gravity and so on, basically most systems we encounter in a physics class, the Lagrangian has a very common form. It is half of the particle's mass times its velocity squared, that is half m x dot squared, minus a function of the particle's position coordinates. This second function, named the potential energy of the particle, is such that minus of its gradient gives the force acting on the particle. The word gradient means rate of change with position. The first term involving the velocity squared of the particle is called its kinetic energy. Why these terms are called so, what energy is in general, we shall cover in a separate video. For now, let's finish this video by using this generic form of the Lagrangian in the Lagrange's equation. Since the Lagrangian L has half m times x dot squared, the derivative del L del x dot yields m times x dot. Then we have the d dt over it, so one more time derivative gives x double dot, the acceleration. This is the mass times acceleration term. The other term is a simple derivative of L by x, the position coordinate. So the potential energy function v of x contributes, giving minus of its gradient, which is the force acting on the particle as we have mentioned earlier. So you see, the Lagrange's equation also tells us that force equals mass times acceleration, as is the statement of Newton's second law. I know this video has been a bit heavy. You see, science is fascinating, but understanding how science works is hard work. If you are still here, I must appreciate your patience. Thanks for your time. Let's meet on the next video where we shall see what energy and momentum really are in context of symmetries of a system. Bye-bye.